Okay, hello everyone. It's pretty full today. What a weekend, right? uh, so we will continue where we left off last time, and that is with trees. The two examples that we went through last time were representing a river system with streams feeding into rivers or merges. Uh, So the main point of tree data or branching data is really just pretty much the same as using linear data. We just happen to have two self-references in at least one of the cases in the data union data definition. So right when we have something is one of, we have two references in there, and this translates in our template, of course. Uh, when dealing with self-referential data, every time there's a self-reference, we have a recursive call. Okay, so one could think of lists or list-like data as basically kind of a special case of trees where we only have one branching. But trees are really at least two self-references. We can have more than two. And what I wanted to something that I didn't finish off last time, so I just wanted to give an example data definition with a tree data structure that combines both a double self-reference with a single self-reference, which still means it's a tree because there's at least one of these. So I'll just do a data type called a tournament. Right, and what we are trying to represent here is what is called, I think, a tournament bracket, right? So when you have a kind of a bunch of competing teams and you kind of eliminate them through rounds, they compete against each other, and every time somebody wins, they continue into the next round. So a game in a tournament is represented simply as a make game with the winning team name and some and two references to the previous rounds or teams, or basically the winning team of the previous game. Then we can have something that's called a bye, right? So this is the case when we don't have think when we basically one of the teams is allowed to sit out around and they progress automatically. So this is usually used to deal with when you have a number of teams that is not a power of two, which doesn't then allow you to eliminate. So this is basically just a way of letting one team to progress to the next round. And then finally we have a base case, which is simply a team name, right? So start with a bunch of teams. We combine them using games. Games eliminate one of the team. The winning team is always propagated. We do allow some teams to sit out certain rounds and not participate. Let me just do the help us struct definitions. We have a game with an winner and a left and right tournament. Then we have a bye with the team, and we have a team with a name. Okay, so even though without make game, right, this would be linear data. It would be just a list of things, not so interesting. But we do have one case that is self-referential, which means that it's branching, means that it's tree data. Even though we also have one case where it doesn't branch. And the only thing I really want to do here is to write out the template for this. Okay, so we have union data. We will have a cont. How many cases in the cont? 3. Yeah. What's the first case? Yeah. Game, huh? Exactly. Following the data definition. The data that we have available is a game winner. We have game left and game right. Right. Game winner is an atomic data, nothing to do with it there. We don't know what we can apply, but game left and game right are themselves tournaments, which means that we apply the template. Second case. Yep. Buy, huh? Buy only has one team, one field, which is a buy team, which is again a tournament, applying the template to it. And finally we have a team, huh, which simply has a name. Okay, still tree data, still the same principles apply to self-referential data. Every time we have a self-reference, we call the template. Twice in the case of game, once in the case for buy. Okay, because there's only one self-reference. The important thing is we are branching in one of them. Any questions? Yeah. Left and right are the branches that led to this current game. Okay, so if I start with teams like Team A and Team B, right, and Team B wins over Team A, I construct something like Team B make Team A B. This means this is a game between Team A and Team B, which was won by Team B. This is roughly what the data is representing. Any other questions? See the chat. Okay. So the question that, or we kind of want to move on today to another use of trees, right? So there's really two uses for trees in computer science. Well, not just two, but I would categorize them as these two for now. So we have data that's inherently tree-shaped, right? So when we want to represent a river system that merges together, we will have tree-shaped data. When we want to represent a tournament where each tournament is preceded by several other tournaments and we kind of join two branches together, we have tree-shaped data. So many, in the more abstract domain, I don't know if you are familiar with a thing called decision trees, right? Where you analyze a decision and being like, okay, if I answer to this question, yes, these are the options that I have. If I answer no, these are the options that I have, and you kind of draw out all the possibilities. So that's tree-shaped data. If you want to represent it in a computer, you are representing a tree. But there's a more abstract, or like use for trees that is not inherently for tree-shaped data. Okay, and the example that I want to use is, for example, imagine that we have 100 names, and we put them in a list, right? And I want to check whether the list contains a given name, right? One of the names. If the name happens to be last in the list, I have to go through 100 names to confirm that it is the case, right? So in the worst case, whenever I have a list, I'm looking for something in the list, I have to go through each element and check, does this element appear in the list? Now, what about I represent this data as a tree, right? Now, I will just do a little bit of hand waving and we will make it concrete as we go along. Now, if I say, okay, I have 100 names, let me split them into 50 and 50 names, right? Then split the 50 into 25, 25, 25, 25, 25. Was it 5 or 4? I don't know. So 4 times 25, right? And then I split them further and further. If at each point I have an ability to decide whether something is in the left or the right portion, I can cut my problem at each step into half. Right? So if I know that the name is in the left half, I suddenly can immediately ignore 50 names out of there. Then if I go further and I know that of the 50 it's in the right half, I eliminate another 25. Right? So I'm doing a much more efficient search by reducing the space with every step, unlike with a list where I'm at each step only reducing by one element. With a tree, what we call a binary tree, so a tree that just branches into two, I can split my search problem at each point into a half, which is a great achievement. Okay, so let's now talk about these binary trees, and what we will talk about primarily is a binary tree that is composed only of two cases. So we either have a leaf that doesn't carry any information, right? In this sense, this is similar to the empty case for a list. Okay, it's just empty, nothing there. And then we have what we call a node of a tree, which carries some information. I will skip that, and has two, for now, and has two self-references. Hence binary tree, branches into two trees. Now, the way we want to use it is to use a number as kind of a key. So think of it as maybe a numeric identifier. And the information can be a name, for example. So like pairing your student ID to your name. Okay. As the interpretation says, make node really just associates a key, a numeric key, with some information expressed as a string, and contains left and right subtrees. This is a very typical definition for a binary tree that carries some information. Okay. Clear so far? A variation of what we've seen before, kind of a simplification, or like bared down to the essence. So here are some examples that I have pre-prepared. We have a leaf, which is an empty tree containing nothing. Then we have a few branching trees, and I want to again draw this as example and visualize what it looks like, so that when we talk about working with the tree, we have a concrete image to work with. So please bear with me while I do some ASCII art. So the root node, which is the top of the tree, I don't know if we introduced this terminology, but the top of the tree is always what is called the root node. The root node here is a 10 assigned or paired up with A. So let me just write it like this, and that one branches into two two subtrees, where on the left we have a node containing 11 paired with B, which itself contains another subtree. On the right we have the S right tree, whose root is 12 with D. So I'll write that out. So I'll just keep on filling this in. Please check me if I'm doing this right. So the 11 has a 9 on its left, paired with C, and a leaf on the right. Then 12 has a leaf on the left, and an 8 with E on the right. Leaves don't branch. Now 9 only has a leaf, and 8 still has a 7 with F and a leaf here, and then the final Okay, I hope I did it right. So this is a kind of a visualization of the tree there, of tree S, with 10 as its root node. Here the leaves and a few subtrees. So this is S left, this is S right, this is S right. And I think that's about all of them that we have named. Okay, hope it's still clear. Okay, let's write down a template for this one. We have two cases there. All right, we either have a leaf or we have a node. Is there anything we know we can do when we have a leaf node? No, doesn't carry any information. So again, it's similar to the empty case. In the case of an actual node, we have four pieces of information. So we have a node key, we have a node info, we have a node left, and we have a node right. Okay. There's some atomic data and some actual data definitions. What can we do with this data? Yeah? Exactly. So we have self-reference in the left and right, which translates into a recursive call to the template and further down the line to the function that we are defining based on this template. Okay. Basic template for binary tree. Any questions so far? Should be clear. Let's try to use this, and let's write a function called a height of a tree. Okay, so we want to compute how tall the tree is. Let's start with some examples, right? So if we have a leaf, the height of a leaf is 0. Okay, that's a tree that's 0 high. Zero high. What's the height of a tree that contains a node and two leaves? Yep. Sorry? No. Yeah. So if it's a tree that just contains two leaves, regardless of what information is there, the height of the tree is 1, okay? Because it has one piece of information and then leaves, and the distance to the leaves is 1. This subtree, where it contains a tree of height 1 on the left-hand side and a leaf on the right-hand side, what do you think the height of this one will be? 2. Yeah, exactly. Basically, what height signifies is the longest path that we need to take to reach a leaf node from there. What's the height of the tree S? Yeah? 3? 4, exactly. Because on the left-hand side, we have a path of length 3, which is the longest one. But on the right-hand side, we have 1, 2, 3, 4 to reach a leaf. So the height of the tree there is of S is 4. Okay, I don't think I have. This would be S left, I think. So if I copy over the template, so we established that the height of a leaf node or of a leaf of a tree is just 0. What is the height of a node that contains two subtrees? Yeah? The maximum of the two, very good. So we take the maximum of the two subtrees, which means we need to get the height of the left subtree and the height of the right subtree. Do we need the key or info? Irrelevant to what we are doing right now. Okay, we have the max of the left and right subtree. Are we done here? Josh? We just had 1, exactly. So every time we encounter a node, that means that we are 1 further away from any leaf on any side, right? And then we just take the longest path between those two, and that will give us a height of a tree. See how many errors I made. Typos, of course. Okay, that's the height of the tree. Okay, so the motivation why I introduced binary trees was to find whether something is contained within some data structure, right? So for a list, we would just read through the whole list. So now we want to define a function contains, which tells us whether some key expressed as a natural number is contained in the given binary tree, and return true if it's contained, return false if it's not there, right? Let me start with the template again. And let me go through an example. So to find out whether something is in the tree, right? So let's say that I want to figure out if 8 is contained. I can see it right there, but how do I actually process this tree and get to it? Get to the answer. Yeah?
You need to pick a side to look at, like we have a left subtree and a right subtree, and then we would check for each.
Yeah, exactly. So the first thing that I need to do, though, is to check whether 8 happens to be the root node of the given tree. And if it's not there, then I just need to look into the left one and look into the right one, right? I look into the left one, is 11 my node? If it's not, I need to check the trees and so on. I go there. Eventually, I check my right subtree, check whether 12 is equal, go to the left, there's only a leaf. Leaf never contains anything, so I can go back, check whether this root node is equal to 8. It happens to be, so I can just return true. Okay. So let's actually fill in the code. So we established that a leaf never contains anything, so I can just return false, in this case simply. What about the node? What do I need to do? Yeah? Okay, so check if key is equal to k. Okay. What else? Josh? Okay. So if I don't need the info right now, I only need the key. If key is equal to, then do something else, do something. We established that I need to look into the left and right subtrees. So I do just that. Okay. So if k is equal to the node key, then what do I do? Yeah? Exactly. So if we start with if, we kind of are led towards returning true if the first argument is true, which is a big no-no. We can simply use OR, right? Because if the key is equal to node key, then this will be true, and OR will be like, okay, I don't even need to know anything else. I can just return true. Otherwise, if it's false, it will try to check whether the left subtree contains the key. If it does, that will return true, and we are still skipping the rest. If it doesn't, we'll check the last one, and the result of the for the right subtree will determine the overall result. All right. So simply is a key is contained in a tree if the current root node contains the key, or if the left subtree contains the key, or if the right subtree contains the key. Okay. Let me check that. And we're good. Any questions about this one? Okay. Now that we checked whether a key is contained in a tree, the next step is really retrieving the data that's associated with a key inside of a binary tree. So let's do just that. So what we want to do here, the final step here, is to write a function retrieve, which, given a key, returns the string that is associated with the key. And for simplicity, we will simply state that we assume that the key actually is contained in the tree, okay? So that we don't have to think about what to return if it Let me copy the template. Okay, the first question is, what do we do for a leaf node? So we just said that we assume that the given key appears in the binary tree. So should we even be able to reach a leaf node here? We shouldn't. We shouldn't, because whenever we have a leaf, that means that we didn't find the key, right? So we need some way of telling the user that they actually violated the contract or violated our assumption. And the way we can do it is by simply throwing an error and saying that key not found. Okay, the way error behaves, I'm sure you can guess, is simply shouting at the user that there was some problem and making the program crash, which we are allowed to do. They violated our contract, our assumption. Okay. Now, what about the case that we have a node? Here we have three possibilities, right? Key is equal to node key. It's the first possibility. K is found in the left subtree, or K is found in the right subtree. Yeah? Mm-hmm. So the first thing, though, is we should check if we already found the key, right? Because if we found the key, there's no point in going to the left or the right subtree. So if key equals this, now what construct do I need to use? We used OR before because we were just dealing with Booleans. Yeah? We could use an if, right? But we really have three cases in here, right? So what we would do is use a nested if, which means we can just use a cont in here. So we have a cont. We already know what the first case is, right? If we found the key, we just want to return the info that's associated with it. So let's just do that. So that's the first case. Now, what was the second case? Can you remind me? Yeah? So we need to choose one. Let's choose left. The reason why we also might want to choose left, it's just because of the order of the fields. Okay, so it's kind of still following the structure of the data. So we check whether the left one contains. If it does, then we retrieve from there. Okay. And we have the final case. This really shouldn't be here. Okay. What is the final case? So we can just do retrieve, but we need to say what the condition is, and in this case we can just use else. Okay, so otherwise we try to retrieve in here. How many typos? No typos. Okay, let's just try if throws an error. Here's a little question. So would it be okay to actually use this as the condition instead of else? Yeah? Yeah. So there's 2 points, I think. So this is completely fine to say, because actually if the key isn't here, if the left subtree doesn't contain the key, then the right subtree should contain the key based on our assumption that the key is actually in there. So if this condition wouldn't fire, we would still get an error, which is fine. But as you say, sorry, what's your name? Brandon. One day I will remember. So as Brandon says, we kind of waste time here by checking if it's still in the right subtree, right? We just want to go in there and retrieve. We exhausted all the other possibilities. So that's kind of the efficiency. The other thing is that if we have contains here, the error that we will get is, go away. Is just that all the questions were false, which is definitely less informative than the nice error that I just threw. Okay, so we really want to, for efficiency reasons as well as for kind of informational value, just be like, okay, otherwise just try to find it there. If we don't find it, then eventually we will hit a leave and we throw an error, which is nicer than actually saying one of the cases didn't apply. Okay. Any questions? Yeah? Uh-huh. So yeah, that's a very good question. So the nested cons con really comes from not nesting templates inside of each other, right? This outer con is here because we are checking the various cases of the template. This inner con is here because it makes logical sense, right? We are checking for the first one, we are checking for the second one, we are checking for this one. We could have just as well replaced it with a nested if and say if key equals to node key, then return this. Otherwise, if contains node left, then do this. Otherwise, retrieve from the right one, which would be another way of expressing the same. Con just happens to be more convenient. Okay, and doing this way and including the else is okay because we are not analyzing some predefined data. We are just doing kind of a three-way decision in here. So this con and this con really fulfills two different roles. It's a good point to raise. Okay, yeah? Exactly, that's the question I was hoping for. Being like, you BS'd us, right? You told us that using trees should be more efficient than going through lists. But here we seem to be wasting work on going through the whole left subtree to check whether the key is there, and then if it's there, we go through it again to actually retrieve the key. If it's not there, we already went through the left subtree and then we go to the right one. So if we have a worst case where the key is on the rightmost kind of end of the tree, we again go through all the elements to find it there, right? So it's absolutely true that this way of finding the information doesn't seem to be much more efficient than doing the list, okay? And the problem why we have this is that we have a relatively expensive way of finding whether one or the other tree contains the node or the key itself, right? What would be nice would be to have a way of simply deciding immediately whether we need to look into the left one or we need to look into the right one, right? Instead of using contains. And the way we can do this is if we think about how we look for things in a dictionary, right? You take a dictionary book. Anybody remembers books still? Good. So you take a dictionary, right? You know that it's alphabetically sorted, right? If I tell you to find me the definition of, I don't know, octopus, right? You don't go opening the book at the beginning and being like A, B, etc., right? You're like, okay, O is like somewhere around the middle. You put your fingers there, open the book, and then you again don't go like, okay, I opened L. Okay, so L, M, and then you know that it's not to the left of the L, so I kind of skipped half of the book already. I go further down and maybe kind of find another place to open the book, and then I kind of recalibrate, either go before or go after, depending on where I open the book, right? And the important property that we use there is the sortedness of the entries in the list. So the fact that they are sorted alphabetically, ordered, which means we have a reliable way to say, okay, the middle of the alphabet will be somewhere in the middle of the book, so I can split my problem into half just by opening the book there. And this leads us to another data structure, which is called binary search trees. A binary search tree is actually exactly a binary tree with an additional constraint. And the constraint is that if we have a node, then all the elements to the left of the node should be smaller than the key in the root node. And all the keys on the right-hand side to the right of the node should be greater, right? And this is not just true for the root node, but if I go to the left subtree, I again have to have this property. When I go to the left, I find the smaller keys. When I go to the right, I find the greater keys. What this allows me to do is to take the root node. If I didn't find my key, and the key happens to be smaller than what I'm looking, the key that I found is greater than the key that I'm looking for, right? Then I know that I need to go to the left, which is this way on your side. So just using this property allows me to do exactly my thing, splitting my problem into roughly half at each step, just like with the dictionary. Okay, so again, the shape of a tree is exactly the same. We just add an additional constraint saying that the property that we want to hold is that everything to the left of the root node is smaller, everything to the right of the root node is greater. The template is exactly the same, still the same data definition. Let me do a quick ASCII drawing here again. He says quick and then takes half an hour to draw it. So we have 10 and I will draw the tree S2 because that's the one that's more interesting. So there we have 8 to the left with B. And we have 11 with D to the right. Then we have 7C to the left of 8. And a leaf to the right. 11 has a leaf on the left. And A13 with E to the right. These branches. This doesn't. This branches. Now 7 just has 2 leaves. 13 has 12 to the left with a F and a leaf on the right. And finally, there's 12 which branches and just has leaves. Okay, now if we check this, whether we actually have a binary search tree, we can see, okay, I have a root node, so everything on the left has to be less than, which is true, 7 and 8 are less than 10. Everything to the right has to be greater, 11, 13, 12, all greater, good. Now the left subtree has 8 as its root node. Everything to the left has to be less than, which is 7, works out. Everything to the right has to be greater, there's nothing, still true. Left subtree 7 doesn't have anything, satisfies this property. I will get to you right away. On the right, we have 11. Everything to the left needs to be less than 11. True. Everything to the right has to be greater. 13 and 12 are greater. Now 13, everything to the left has to be less than 13. 12 seems good. Everything to the right has to be greater. There is nothing greater. True as well. 12 only has empty leaves, so trivially satisfies this. Yes, Brandon?
So if you had like you have 10 and you have 11, you did have something in the left branch of 11, but it also has to be greater than 10.
Yes, exactly. So to put something in here, it would have to be greater than 10 but less than 11. Okay, so if I didn't use naturals as my keys, which I think I did, it would be like 10.5 would fit in there, for example. Any other questions? Okay, let's do retrieve using the new property. So again, a leaf doesn't contain any key, so we just throw an error because whoever is using this function better checks that it satisfies our assumption. We still get the same kind of data here. So if the easiest one, if we found our key, so if key equals to node key, then we just return the info. That doesn't change. It's simple. Then we need something here, and we need something here. And we do, of course, retrieve from the left or retrieve from the right. Okay. Now, what are these two conditions? Josh? So the first condition is if k is greater than the node key, like this. Okay, is it greater? Yeah? Yeah, exactly. So the left-hand side should contain the keys that are smaller, right? So if the key that we are looking for is smaller than the current root node, which is node key BST, then we need to go to the left. Okay, so it's actually flipped around. We need to take care what we are comparing to what. We are checking whether the key that we are looking for should be to the left. So if it's less, should be to the right if it's right. And the way I wrote it actually leaves the angle bracket to point in the direction that we need to look into, which is kind of neat. Okay. But again, in this case, no, actually in this case, this will work, right? So if it's greater, we go to the right-hand side. It needs to be in the right-hand side if it's greater, so we throw an arrow if it's not there. If it's smaller, it needs to be in the left-hand side, so again, we throw an arrow. So this condition, this three-way condition actually covers all the cases without having an else here. And yeah? If we left this as greater than? Uh-huh. So this would always return an error if we get a tree that actually satisfies this condition, right? Because if the key is greater than the root node, then it needs to be in the left-hand side, but we are always looking on the right tree. So we would never get a result, and then if we flip this, then we would again look over in that. Okay, so one has to be careful about what am I comparing to what. Does this make sense? Let me try to run this. Okay, the test passed. What did we have? So if I want to retrieve something from the left-hand side and see whether it throws an error, so that's 2, and let me look for 1, which should be somewhere here, right, to the left of 7. Wrong key. 2, 7. Why did I write the 1 is the one I wanted? Okay, that seems to work fine. Now something that should be to the right of 13. Let me check that, and let's try like 23. Key not found. So we, in both cases, we reach the leaf node. Okay. Now let me think about what this does for me. Okay. So one neat trick to know that you have a good valid search tree, and actually this will be helpful in explaining things, is to simply draw a line right down from each of the elements here. And if I do that and write the elements in that order, if you notice, what I get is a sorted list. Right? Now, let's think about what is the worst case for searching in this list. When do I get the worst performance for an element that is actually in the list? Yeah? Well, I'm starting from the beginning of the list always, right? But you're right with the 13. If I'm looking for 13 in this list, that means that I have to go through each element to actually find this. So I go check this one, 1, 2, 3, 4, 5, 6. Okay. How many steps does it take me to find 13 in this tree? 2? What is the answer 12 to? How many steps does it take me to get to 13? Yeah? Why 2? Start at 10, that's one comparison, 11, another one, 13. That's the third one. So it takes me 3 steps, right? Still much better than 6, right? What's the worst case for the tree? Yeah? The longest path, right, to the leaf. Or and the longest path to actually find the valid element is to find 12. And that takes me 4 steps. 1, 2, 3, 4. Right? In the list, I have 1, 2, 3, 4, 5. Still a better performance. Now, if I'm dealing with lists, the worst case performance is always as many steps as there are elements in the list. Right? If I'm looking for the last element, I will have to go through each element to actually find it. What would you say is the longest or is the worst case expressible as for a tree? Yeah? The height of the tree, exactly. So the one property when we think about actual efficiency is with lists, we don't have anywhere to go to, right? If we have a sorted list, the worst case will be always finding the last element. But with a tree, there are multiple valid binary trees that are search trees that satisfy our property, right? I can build a tree out of this list by simply doing this. I won't do the whole thing, but I hope you get the picture. So if I put leaves on here and on here and on here, etc., right? I still get the property because there's always an empty list to the left. So it's always satisfy the property that only smaller elements are to the left and only greater elements are to the right, which, like, if I continue this, will be always true because I get 7, then to the right is 8, to the right is 10, to the right is 11, to the right is 12, to the right is 13. And I end up with exactly the same performance as the list because the height of my tree is the same as the length of the list that I was putting there. So what we really want to end up with is with a tree where the elements are distributed kind of evenly. Okay? The ideal, what we really want is what is called a balanced tree, where the longest path is the smallest possible path. Okay? And really the ideal thing is, because we are splitting the problem into 2, the actual ideal height of the tree is the logarithm of the number of elements, but that's not really important. Okay. So the shape of the tree matters. There are multiple trees that satisfy our property, but not all trees are as ideal as others. That's one thing. This is given by the fact that the performance depends on how tall our tree is, right? Because at every step we kind of split into half, and the height of what we have left with, what we are left with, is as far as we can go at any point. So that's one thing. The other thing that I wanted to point out: what if I do something like what if I want multiple elements with the same thing? Okay, so what if I want a tree that contains multiple keys that are the same? My current definition doesn't allow this because I say everything that's smaller needs to be to the left, everything that's greater needs to be to the right. In general, what we use is usually say everything that's less or equal to goes to the right, or everything that's greater or equal to goes to the right, so that you do allow this. For our purpose, it doesn't matter because we only find one as we go through the list. Through the tree. So even if we insert this one, it doesn't really affect the performance or anything. But just wanted to point out that you might want to have trees where you have multiple elements. And trying to remember if there's something that I'm forgetting. So that's about it with how we actually use binary trees for searching for things. What I won't start with it now because we are at the end, but what I want to do next time is how do we actually get binary trees that satisfy this property, right? Because right now we were just given an example, and that example, before I modified it, at least, nicely satisfied that property, and we could use it as a binary search tree. It had that nice property where at each step we split the problem into a half. So next time we will look at how do we build binary search trees. Are there any questions about these? Okay, awesome. Thanks for coming. Thanks for listening. Have a good Veterans Day. I'll see you on Thursday.
I emailed you about a group project thing that I have to do. It's just like looking over some product.